Okay, so now that we know this is a zero order reaction, we can answer some questions here. So it says state the differentiated rate law. That's going to be rate is equal to K times the concentration of N2O raised to the 0 power, which is 1. So that's simply rate equals K. If you wrote it either way, that's fine. Integrated rate law is going to look like this. The concentration, of N2O is equal to negative KT plus the concentration of N2O at time 0. And now we want the value in units of the rate constant K. So we'll do it both ways just to make sure that this works. So we'll get it by solving, and we'll get it by getting the slope from the graph. So we'll pick a time. I'll just pick 10 seconds. We have a concentration of 0.0394. And so when we do this to solve for K, and let's take the negative sign with us, that means that this is going to be N2O minus N2O at time 0 divided by negative time. And I took the K with us, or the negative sign, so just leaving it K. It doesn't really matter how you do it, because if you do it the slope way, you're going to get a negative K anyway, but we just want the raw value. So let's plug some stuff in so we know what we're doing here. This is 0.0394 moles per liter minus 0.0447 moles per liter, and we picked 10 seconds. So nothing's going to cancel, and so our units are going to look like moles per liter seconds. And here is our calculator. We'll say 0.0394 minus 0.0447, and we're going to divide that by 10, which we don't really need a calculator for, but that's okay. 5.3 times 10 to the negative 4, and it is a negative number because that's what this looks like, but we should have divided by negative 10 seconds, so 5.3 times 10 to the negative 4. Let's do that by getting the graph and see what we have. So the graph looks like this. We're going to go to stats. We're going to take calculation and do a linear regression on L1 versus L2, looking for something close to 5.3 times 10 to the negative 4. This is going to be negative because it's a negative slope, and that is not bad at all. It's very close to 5.3 times 10 to the negative 4. All right, and our units are moles per liter per second. Okay, so now we want the half-life of the reaction. And it's good to get these committed to memory, but I'm not so good at it myself. And so the half-life equation for a zero-order reaction is concentration of A at time 0 divided by 2K. So let's plug that in right here. So T1/2 is going to be equal to our concentration at time 0 divided by 2K. You know the concentration at time 0, 447 moles per liter, and our constant K is 5.3 times 10 to the negative 4 moles per liter per second, and moles per liter are going to cancel, leave our answer in seconds. So we'll say 0.447, 0.0447 divided by the quantity of 2 times 5.3 times 10 to the negative 4. This is our half-life, 42 seconds, 42.17 seconds. It's probably a good idea to verify that this time makes sense. So looking at our data, if this is 0.447, half of that, we'll call that 0.045, half would be 0.0225. and that would land somewhere 0.0225 in between here. So that lines up perfectly. So I'll accept that answer. At what time will the reaction be used up? In other words, at what time will the concentration of N2O be 0? So we're going to take our equation. N2O is equal to negative KT plus N2O at time 0. And we're going to solve for T. And so when we solve for T, it's going to look like this. N2O minus N2O at time 0 divided by, and let's keep the negative sign over here, negative K. Well, at time 0, the concentration of N2O is, when the reaction is used up, the concentration of N2O is 0. So let's just plug everything in. So let's keep our units consistent. This is 0 moles per liter. And our rate constant K, negative 5.3 times 10 to the negative 4 moles per liter per second. Moles per liter are going to cancel, leave our answer in seconds, which is what we want. So going to our calculator, we'll say 0 minus 0.0447. Yes, it is 47. 47 divided by our rate constant K, 5. Whoops, let's make that negative just so that the answer comes in positive. Negative 5.3 times 10 to the negative 4. Ladies and gentlemen, our reaction will be used up in 84 seconds. And this answer should make some sense because it was halfway used up at 42 seconds, which means it should be all the way used up at twice that, or 84 seconds. Okay, last one. Chemical equation for the decomposition of hypobromite. Yikes. All right, well, let's get our calculator ready for this one. So we're going to clear all the lists, and that way we're ready to enter some data. So now that we got the hang of this, we're going to go pretty quickly. So we've got time 0, 20, 40, 60. Yeah, go quickly and you make mistakes like I did, 80 and 100. And here as our concentration, L2, we've got 0.750, 0.408, 0.280, 0.213, 0.172, not negative 172, 0.172, not 0.172 either, and 0.144. Okay, let's graph this stuff. We're already set up to graph L1 versus L2, but I don't think this is going to be a straight line. Let's zoom to the data, which I thought I already had. Did I do this right? Let's make sure. It's not on. That's why. Now we can graph. Zoom 9. Oh my goodness, that is very much not a straight line. And I don't like that data point, so I'm just going to double check that my data is as it should be. And this one is not. It should be 20. So let's try that again. Much better, but it is not a straight line. So let's go back to our statistics. Let's edit this and let's instruct the calculator to take the natural log of everything that's in L2. And now we'll graph this. We'll turn this one off and we'll turn this one, which we're going to construct to be a plot of L1 versus L3. We'll turn this one on. And let's graph, zoom to the data. Not a straight line either. So we can simply default that this is a second order reaction, but I like to check, ladies and gentlemen. So let's go to our data. And let's set up one more. We're going to tell the calculator to take everything that's in L2 and invert it. And let's make sure that this is on. Or you could simply, and here's another one, you could simply go to plot 2, which is already on, and tell it not to graph L1 versus L3, but L1 versus L4. So you don't have to go all the other stuff. So now let's graph. Zoom 9. Thought it's going to be a second order reaction, and that is very much a second order reaction. So when it says state the differentiated rate law, rate equals the concentration of K times the concentration of BRO raised to the second power. That's the differentiated rate law, and the integrated rate law is going to look like this. At time 0. And let's get the value and units of the rate constant K. So there's no negative signs to worry about. We'll pick a time. I'll pick 20 seconds and 0.408. Or we could simply solve using the slope, but that's okay. We'll do it like this. So we're going to have, at 20 seconds, we'll have 1 over 0.408 moles per liter minus 1 over 0.750 moles per liter divided by the time we picked 20 seconds. So our units, when we invert moles per liter, are going to be liters over moles seconds. And we could just plug this right into our calculator. So we'll say the inverse of 0.408, not squared, inverted. Oh, I didn't want that. Delete. And I didn't want this. Delete. And delete. Better. Took a little fixing. Now minus 0.750. Invert, and we'll take that and we'll divide that by 20 seconds, and this is going to be our value units of the rate constant K. We'll call it 0.056 liters over moles seconds, or you could simply, that's not what I wanted, run a linear regression on this data, provided of course that you tell the calculator to do the linear regression on L1 versus L4. And we should get something pretty close. Dead on the money, 0.056 right here. So that looks good to me. And let's get back to this. All right, so there's our value in units of the rate constant K. What's the half-life? Half-life of a second order reaction looks like this. And I have a hard time keeping these straight, so it's a good idea to keep your so we'll say 1 over K, 0.056 liters over moles seconds, and our concentration at time 0, which was 0.750 moles per liter, and that's going to leave our answer in seconds, which is what we want. So I'll tell the calculator to take 0.056 and multiply this by 0.750, and then I will invert this to get our half-life. And before we do that, let's predict. 0.750, the half-life is 0.0375, so it should be somewhere between 20 and 40 seconds. Do we get that? 23.8 seconds, which is dead on the money.